Boom, ladies and gentlemen, welcome. This is Juliban Schools, powered by Quintessence by Juliban. Okay, and in today's chapter, we're going to be looking at chapter 10, that is AC circuits. In the former chapter, we looked at magnetic field and the various aspects of magnetic field. If you have not watched that video or listened to that podcast, do well to check our playlist and you will see them there. Okay, magnetic field in details, like it's really detailed, so you have no fear dealing with magnetic field having gone through that video or podcast. All right, so in this chapter we are going to be looking at AC circuits. Okay, the amazing AC circuit. AC circuit happens to be a very interesting chapter, and it is one of the chapters you will always want to go through over and over again because of how interesting it is and how it relates to every day by day activity you do when it has to do with power, light, electricity. Okay, all right, so basically this chapter will be divided into four broad topics. Number one, we're going to be talking about the root mean square concept. Then number two, we're going to be talking about AC circuit diagrams, and then finally we'll focus on power, and then finally on transformers. Okay, so basically that is that. And however, it's going to be adumbrated into a total number of facts, which I tag 20 facts. 20, yes, a total of 20 facts in the whole of AC circuit. If you are conversant with these 20 facts, be rest assured that AC circuit is nothing but a very easy topic for you. All right, so let's get started. AC circuits. What is an AC circuit? An AC circuit is simply a circuit that comprises two basic parameters. Number one, circuit components like capacitors, resistors, inductors, as the case may be. And then secondly, a source of power. I mean, if you have elements in a circuit without power, I mean, there is no AC there. There is no AC. AC is alternating current, okay? Good. So alternating current in the sense that the current varies. If you want to see the diagram of, in fact, let me show you the diagram. Okay, good. Now that you can see the diagram, if you check this diagram, it's actually sinusoidal. That is the direction motion of current from AC source. Okay, sinusoidal. That means it goes up, comes down, goes up, comes down in that coily manner, and it continues to go. Now the face up is positive, the face down is negative. It may interest you to know that the light you see that appears stagnant when you switch it on at night actually is not stagnant. It goes off and on, off and on, off and on within nanoseconds, and you barely can notice it, right? That is a gospel truth. That is AC circuit for you. So the first half is always positive. That is current and voltage, or current or voltage is always positive. The second half is always negative. So it constantly goes on and off, on and off, on and off, on and off. But because the rate at which it goes on and off is very fast, you don't notice it. You feel like it is stagnant. The only type of current that is stagnant, that does not go off and on, is DC current. And now look at the diagram. A DC current diagram actually follows one direction. And if you check it, it's positive, positive, positive. Voltage is positive always, current is positive always. It does not go off and on like you have in alternating circuit. Hence, it is called direct circuit. Okay, good. And because it goes through such sinusoidal movement, that is where you have what we call angular velocity. Okay, and angular velocity is given by 2 pi f. F is the frequency, and of course frequency is the reciprocal of period, so W can be 2 pi over t, representing your angular velocity. So now that takes us to the 20 amazing facts in AC circuits. AC circuit, actually, when you use the word AC circuit, it's a little bit it sounds a little bit contradictory, but let it go. So the basic facts, 20 of them. We start with the very first fact there, which is the square law of deflection. That's the first fact. The square law of deflection states that the angle of deflection by a needle in either a galvanometer or a voltmeter or whatsoever it is directly proportional to the square of the current passing through that instrument. That is the square law of deflection. The angle of deflection directly proportional to the square of the current. So theta becomes directly proportional to I square, as the case may be, right? Good. That's the first fact. Now that takes us to the second fact, which is voltage and current in a coil. What is the instantaneous voltage? What is the instantaneous current in a particular coil. Instantaneous voltage is simply given by V equals V naught sine WT, while instantaneous current is given by I naught sine WT, right? Now, when you talk about instantaneous current, what do you mean? The current at a particular instant time. What is the current flowing through a circuit on the 17th second? That is instantaneous current. What is the voltage in a circuit at the 18th second? Instantaneous voltage, right? Now the I naught there signifies peak current, while V naught signifies peak voltage or maximum voltage, as the case may be. Then W, of course, angular velocity, and T there represents the time. Okay, so it is also very, very important for you to know that current and voltage do not, in some cases, hit their maximum point, their peak voltage at the same time, even though they have the same frequency flowing through them. That's the gospel truth. However, there are some cases where voltage and current can actually hit their peak at the same time, even though they have the same frequency. And that happens in a purely resistive circuit. We are going to see that as time goes on. So that takes us to the second fact, and the second fact is the concept of the root mean square. It would have been very easy for me to just tell you that root mean square is simply the square root of the mean of the square of all the currents in an AC circuit, or all the voltages in an AC circuit, or all the instantaneous current or instantaneous voltages in an AC circuit. That is root mean square. But however, there are rooms for detailed explanations, okay? So when you talk about root mean square, this does not actually mean the maximum value of current or the maximum value of voltage. That's a misconception. A lot of people mistake root mean square of current and voltage to be their peak. No, hell no. It is simply the algebraic sum, in fact, the average. When you find the algebraic sum of all the instantaneous currents, square them, divide them by their number to get their mean, then find the square root of it all. That gives you the root mean square of either the current or the voltage. Okay? So, and it is always represented by IRMS or VRMS, as the case may be. This is the average current or the average instantaneous current or voltage in a circuit. And that is exactly the value you will see when you take your multimeter and test the amount of voltage running through a circuit. If it is giving you 230 volts, that 230 volt is not instantaneous voltage. No, it is not peak voltage as well. No, it is actually the square of the instantaneous voltages put together, divided by the number of those voltages, and then rooting it all. That gives you 230. So the voltage you see in your socket is the root mean square value at that point in time. Okay? Same thing with current, as the case may be, in any instrument you use to find that definition. In another language, root mean square actually is simply the power dissipated in a DC circuit being equal to the power dissipated in an AC circuit. When the power dissipated in a DC circuit happens to be equal to that of an AC circuit, you can have root mean square value from that, and you can derive that accurately. So that takes us to the next parameter there, which is the relationship between root mean square, peak voltage, and peak current, as the case may be. Now, it's important to know that IRMS is simply the ratio of the peak current to root 2, and VRMS is the ratio of the peak voltage to root 2. And if you're looking for the maximum current or the peak current, is simply root 2 IRMS, while V naught is simply root 2 RMS, as the case may be. Now that takes us to circuit diagrams. Yeah, circuit diagrams for purely capacitive circuits, purely inductive circuits, purely resistive circuits, as the case may be. Now, when you talk about a purely capacitive circuit, what do we mean? A purely capacitive circuit is simply a circuit that comprises only a capacitor. That's all. And there may be a source of power. Okay? If you look at that diagram, that sinusoidal you see in between, that is the sign of AC. Okay? Good. So if you have a capacitor, take your wire, connect it directly to your AC source. That's a purely capacitive circuit. And in such purely capacitive circuit, the instantaneous voltage at any given time is given by V equals V naught sine WT. V, of course, is the instantaneous voltage, while V naught is the peak voltage at that point in time. And W is the angular velocity. And then, of course, you know W is equal to 2 pi f. So V becomes V naught sine 2 pi f t, as the case may be. Now, to determine the current in a purely capacitive circuit, something must be taken into consideration. When current flows through a capacitor, what happens? Of course, it stores charges, right? And the charge stored is Q equals to CV. Now, if you make V the subject of the formula, you have Q over C. And substitute it in the formula for the instantaneous voltage in a purely capacitive circuit, you have Q becoming CV naught sine WT. Okay, and this is the quantity of charge. For you to now get the current from the quantity of charge stored in such capacitor, you differentiate. Of course, if you differentiate quantity of charge with respect to time, that gives you current, okay? So differentiate CV naught sine WT as well. So you have I becoming the instantaneous current at that point in time being equals to CV naught W cos WT, okay? Beautiful. So basically that is that. And this formula simply tells you that current is directly proportional to frequency inside the W and also directly proportional to capacitance and voltage, which is the peak voltage. Boom. So that takes us to the next fact there, which is the fifth fact. And in the fifth fact, we are going to be looking at the reactance of a capacitor. What is a reactance of a capacitor? In quotes, one can take reactance to be opposition, okay? You can, in quote, call it the resistor of a capacitor. Let me use that language, but that is not actually what it means. So the reactance of a capacitor is simply given by the reciprocal of the capacitance times the angular velocity. That is the reciprocal of CW. And that gives you 1 over 2 pi f, okay? So for you to calculate that, impute that into the formula of the instantaneous current. That is to say, you drop down the CW to be a reciprocal at the bottom, and then substitute your XC to that. XC represents the reactive capacitance, okay? Then you will have the current becoming V naught all over XC cos WT. Okay, so if you're asked to calculate the reactive capacitance, you can always make that the subject of the formula. And if you plot a graph against capacity, reactive capacitance and frequency, it will give you that inverse proportional graph as you see there, without the two terminals meeting each other at the top and the left. Same thing with reactive capacitance and capacitor, and taking frequency constant. It gives you that sinusoidal diagram you see there. So that takes us to the sixth fact, which is the voltage or the current in a purely inductive circuit. Of course, as we have already displayed, a purely inductive circuit is a circuit that contains only an inductor, okay, connected to an AC source. And of course, for you to calculate the amount of voltage in such system is a little bit technical. Now, why is it technical? Because in a purely inductive circuit, an inductor actually is simply a coil that has been taken into several number of turns, then connected to an AC. Whenever you take a particular wire and use it to form a kind of solenoid, connect it to a source of power, there exists an induced voltage, induced EMF by the coil, by the inductor. That's what they call inductor. So the induced voltage in that coil happens to move in an opposite direction to the direction of the coming voltage. Now, when this induced voltage happens to be equal to the coming voltage into the coil, we call it self-inductance. However, it is also important for you to know that this induced voltage in the coils is called back EMF. So it goes in the opposite direction so as to oppose the coming voltage in the system. And when this coming voltage happens to be equal to the back EMF now is expressed as L di over dt. That is the back EMF, L di over dt. That is the one opposing the voltage coming from your socket. So when they happen to be equal, you refer to that as self-inductance. So for you to calculate the voltage, the instantaneous voltage in a purely inductive circuit, you must use the concept of self-inductance. And that is to say, V becomes equal to L di dt. And then at that point, you make your substitutions. The I there becomes I naught sine Wt, and then differentiate accordingly. Then you will have V to be equals to I naught Lw cos Wt, where Lw represents your inductive reactance, okay? Inductive reactance XL becomes equal to Lw. And of course, W is 2 pi F as the case may be. So that gives you the instantaneous voltage at any point of time. Now, what about the instantaneous current at any point in time? We still use the concept of the back of self-inductance. So now L di dt becomes equal to V, okay? And V, we already know V to be V naught sine Wt. Substitute it in that formula, take dt to the other side, integrate both sides, and if you do that mathematics properly, you will discover that your instantaneous current becomes minus V naught over Lw cos Wt. And of course, Lw is XL, so you're going to have minus V naught over XL cos Wt. Okay, so and this formula is pretty similar to that of a purely capacitive circuit. Yeah, purely similar. If you remember, in a purely capacitive circuit, current is simply V naught all over XC cos Wt. Now, in a purely inductive circuit, I is equals to V naught all over XL cos Wt. Now, there is a negative sign. That negative sign simply means opposition to the flow of current in the circuit. Very important. Take note of that. And then if you draw a diagram of reactive inductance to frequency at constant inductance, you have a direct proportionality. And reactive inductance and inductance is also a direct proportionality at a constant frequency. So that takes us to the next one. One may ask, we have been discussing purely inductance, pure capacitance. What about pure resistivity? Well, in a purely resistive circuit, though your textbook didn't cover this part, in a purely resistive circuit, instantaneous voltage is simply V equals to V naught sine Wt, okay? There's no big deal about it, right? Now, if you're looking for the instantaneous current in a purely resistive circuit is simply I equals I naught sine Wt. So no much work to do there. I think that's the reason why your textbook omitted that amazing part. So that takes us to the seventh fact, which is the phase angles in a purely capacitive circuit. What is the phase angle in a purely capacitive circuit? Of course, we already know what a purely capacitive circuit is. When current flows through or voltage flows through a purely capacitive circuit, what happens between voltage and current? Are they out of phase or are they within phase? When you say they are out of phase, what does it mean? It simply means that one is lagging while the other is leading. Are they within phase? If they are within phase, what does it mean? That means nobody's lagging and nobody's leading. Now, the gospel truth is that in a purely capacitive and a purely inductive circuit, both voltage and current are never in phase. They are always out of phase. In a purely capacitive circuit, voltage is always lagging behind while current leads. When you say voltage lags, it means voltage is at the back of the current at an angle of 90 degrees, which is pi over 2. Okay, so it is always at the back while current is always, edging it with 90 degrees forward as well. And then if you see that graph over there, you see that voltage is behind while current is in front. And if you do that in a Cartesian plane, you discover that because voltage is lagging, VC is facing downward, the R is facing downward, while that of the current is facing to the right towards the x-axis, okay? So, and if you get the formula, if you need the formula for the instantaneous voltage in a purely capacitive circuit, V becomes V naught sine Wt minus 90 degrees. Why the minus? Because voltage is lagging, okay? While current is leading. That's the essence of the minus there, because of the lagging of the voltage. All right, that takes us to the first angle in a purely inductive circuit. In a purely inductive circuit, voltage and current are out of phase. For the matter of fact, voltage is now leading while current is now lagging at 90 degrees, okay? You see the diagram there. Because current is lagging, because voltage is lagging, voltage is leading, of course, it faces upward. XL is upward, while I is facing towards the x-axis towards the right. And the formula for the instantaneous voltage is V naught sine WT plus 90 degrees. Why the plus? Because voltage is leading. Okay, good. Now, but in a case where you are talking about a purely resistive circuit, what happens? Current and voltage are in phase. In fact, in some texts, they will say current and voltage are in step. Yes, they will use that word in step, right? So they are in phase. No one is ahead of the other. No one is leading. No one is lacking, okay? The phase angle between them is equal to 0 degrees. In fact, V and I are parallel to each other, right? So if you see the diagram, the sinusoidal voltage is above, current is below. Mind you, voltage and current meet their peak at the same time. Yeah, they hit their peak at the same time. And then also they move in that manner. And then if you draw the other one, you see them moving in that direction. And that is why the instantaneous voltage in a purely capacitive circuit is simply V naught sine WT plus 0 degrees. Why? Because there is no angle between them, okay? And when you solve that properly, your V becomes V naught sine W, right? Good. Now that takes us to circuit diagrams. Circuit diagrams in terms of combination. Now we're looking at trying to combine capacitors and resistors, inductors and resistors, inductance, resistance, and capacitance together. So that combination, what will come out of it? That is exactly the next stage we are. Now, mind you, if you check this arrangement, you discover that a resistor is common to all these arrangements because resistors are the sources of power, okay? Any circuit that has no resistor actually does not absorb power. Resistors are pretty important. All right, so let's take the first one there, which is the CR circuit. A CR circuit simply means a circuit diagram made up of a capacitor and a resistor connected to a source of power. That's a CR circuit. C for capacitance, R for radius. Okay, so when you have such a circuit, we can potentially calculate instantaneous voltage, impedance, instantaneous current, phase angle, and even power. Okay, when you have such kind of combination. So let's start with instantaneous voltage. First, it's important for you to know that in a CR circuit, of course, we are talking about capacitor now and resistor. And capacitor, if you remember, in a capacitive circuit, in a purely capacitive circuit, voltage lags, okay? So VC will be pointing downward, while your I will be pointing towards the VR will be pointing towards the X direction. So by so doing, you can actually get the resultant of those two vectors to be your instantaneous voltage to become the square root of VC squared plus R squared. And when you factorize I outward, outside, you have V equals to I root X squared, XC squared plus R squared. Okay? So by the time you divide that I with the instantaneous voltage, it gives birth to what we call impedance. And impedance is actually the opposition to the flow of current, okay? It's another name for resistance, but a more mature one because the system is not just a purely resistive circuit, okay? So it is measured in ohms. And on that note, your impedance Z becomes the square root of XC squared plus R squared. Okay, good. So as for the instantaneous current, is simply I equals V over Z. So V is there, and then your Z is XC squared plus R squared root, as the case may be. Then the angle, the phase angle, of course, if you remember your concept of theta being equal to the tan inverse of y over x, y-axis now is your VC, which is in quote your XC now, while the x-axis is your R. You will now have your the phase angle to be the tan inverse of XC all over R. Okay, good. Then for the power dissipated by a CR circuit, although you won't see this in your textbook, very important you take note of it. The power dissipated by an RC circuit or CR circuit, as the case may be, is simply IV cos phi. Yeah, IV cos phi. And the I you are talking about is root mean square. V is the root mean square as well, which is equivalent to your instantaneous value there. And by the time you substitute that, you will have P to be equals to VI cos phi. Cos phi there is the power factor rating, where phi is the cos inverse of R over the impedance, okay, which is Z. So that takes us to the LR circuit, or RL circuit as the case may be. Of course, an RL circuit is a circuit diagram that comprises an inductor and as well as a resistor, okay? So because in an inductor, current lags while voltage leads, you discover that your XL will be pointing upward, okay, because it is leading, while the current will face the direction of the resistor, okay? So the middle line, which is the resolution between them, is your impedance, okay, or your voltage as the case may be. So V becomes the square root of VL square plus R square, or square root. Then the impedance becomes the square root of XL square plus R, or square root as well. Then if you want to calculate the instantaneous current, there is simply V over Z, which is V all over the impedance. Then the phase angle is simply XL all over R, tan inverse. And then of course the power factor, or the power in an RC circuit, is IV cos phi, where cos phi is your R over your Z. Okay, that's phi, not cos phi now. So now that takes us to the amalgamation of the three sets combined, and that is the RCL circuit, okay? The RCL circuit, very important. An RCL circuit comprises all three components put together connected to an AC source: inductors, resistor, and capacitor. Now, first, for you to determine the voltage flowing through the system, you will need to know who is lagging and who is leading at a particular point in time. Okay, let's start with the inductance. When current flows through an inductance, or voltage flows through an inductance, you discover that in an inductance, or in an inductor, voltage leads, okay? And because voltage is leading, you have your SL facing upward towards the positive y-axis. While in a capacitor, because voltage lags, your VC will face downward, which is also equivalent to your XC facing downward because it is lagging in a capacitor. Okay, good. While towards the x-axis, you have your resistor and current because they are always in phase, right? Good. Now, two things can happen here. Number one, it is either the inductive reactance is higher than the capacitive reactance, or the capacitive reactance is higher than the inductive reactance. When the inductive reactance happens to be higher than the capacitive reactance, both arrows will face towards the positive y-axis such that you have XL minus XC, and then on the x-axis you have R, which is the resistor, and then the resultant, which is the voltage now, or the impedance as the case may be, becomes V equals to the square root of VL minus VC all squared plus R squared, right? And then this is for when capacitive inductance is greater than, that's a capacitive inductance, when reactive inductance is greater than capacitive reactance, as the case may be. So, but when it happens to be the other way around, where capacitive reactance now is greater than inductive reactance, then you discover that both arrows will face downward. XC minus XL becomes towards the negative y-axis, and then you have your R facing the x-axis, while the resultant is your voltage or the impedance, as the case may be. So on that note, you discover that your voltage becomes I bracket the square root of V of XC minus XL all squared plus R squared all root together. So for the impedance is also going to follow suit. You see that there. Same thing with current. So for current, you have two formulas for current. When inductance is higher than capacitance, the current is V all over XL minus XC all squared plus R squared all root. And when inductance and when capacitance is greater than the inductance, you have your V to be equal to the square root, that's divided by the square root of XC minus XC all XC minus XL all squared, and then plus R squared as the root. The same thing goes with the first angle. Boom, you have it there. The power factor remains the same, okay? IV cos phi, where your phi is simply the ratio of R to the impedance. Now the big question is, what will happen when XC becomes equal to XL? We have been talking about XL greater than XC, XC greater than XL. What happens when they become equal? In other words, what happens when inductive reactance become equal to capacitive reactance? resonance takes place. Resonance takes place. And what is resonance? Resonance has to do with maximum output of current. When current is maximum, resonance is bound to occur. Maximum current. That is the number one fact. Maximum current. So at resonance, capacitive reactance becomes equal to inductive reactance, such that XL becomes equal to XC. XL, as we saw before, is WL. XC is the reciprocal of WC. Substitute 2 pi F for them, and then take note, the value of W will now be 2 pi F naught. F naught there represents resonance frequency. And when you make the subject of the formula properly, you have the reciprocal of 2 pi root LC. And that is the resonance frequency in such a circuit that have inductive reactance being equal to capacitive reactance. Now, we go to the 14th fact, which is what happens at resonance. 4 things happens at resonance. Number 1, current is maximum such that at any frequency below or above resonance, current becomes less. Yes, if you check the diagram, you discover that current is maximum at the peak, and then both of them flushes downward towards the other edges. So at that peak, that is where resonance takes place. If you go a little bit on the left, you are off resonance. If you go a little bit on the right, you are off resonance. So at maximum current, resonance occurs. The number 2 things that happens is that at resonance, impedance is minimum. Oh yes, impedance is minimum. If you write the formula for impedance, XL minus XC all square plus R square all root, because they are now equal, if you find the difference between them is 0. So your impedance automatically becomes the square root of R square, which is R, and that's minimum. That's 2. Then number 3, the circuit acts as a purely capacitive, as a purely reactive circuit, because it is all about the resistor now. The capacitance and the inductance are equal, so they cancel each other. So the circuit becomes purely resistive. Then number 4, the phase angle at resonance is equal to 0. Oh yes. Theta is equal to the tan inverse of XL minus XC all over R. By the time you substitute those values and subtract, because they are equal, you get 0. And the tan inverse of 0 is 0. So at resonance, current is maximum, impedance is minimum, resistance is purely, the circuit becomes purely resistive, while the phase angle is 0. And that takes us to the 15th fact, which is the applications of resonance. Resonance can be applied in tuning of radio receivers, okay? You find that applicable in your radios and TV sets. First, a radio set, it may interest you to know that a radio set receives so many signals, yet it makes sense at a particular instant time. It's just like someone speaking to you. You are trying to decode what the person is saying, and then you have 10 people speaking to you at the same time. Can you make sense out of those 10 people? Certainly not. Why? Because all of them speaking together will sound to you as noise. But a radio set receives so many frequencies, so many resonance frequencies from different stations, yet makes sense to you when you tune to a particular frequency. Now, if you are told that the radio station of Man Around Town, for example, is 92.3 FM, it simply means that the resonance frequency of Man Around Town, or ITV, as the case may be, is 92.3 megahertz. That is the maximum frequency at the maximum current. That is for that particular station. Others is 92.7. Others is 101.3. These are their resonance frequencies. When you tune to each resonance frequency, you listen to what the station is saying clearly. Okay? And that is why at times when you are tuning, you hear some sound. At a point, it becomes very clear. You stop at that point. Why do you stop at that point? Because that is the point where current is maximum. Okay? And the circuit becomes purely resistive. And then, of course, the phase angle is equal to 0. So at that point, you listen very clearly, as if nothing was going on in the system. And when you are tuning, do you know what you're actually doing in the physics realm? What you're actually doing is, as you're tuning, you are regulating the value of R root LC in that resonance frequency. You are regulating the inductance as well as regulating the capacitance. Of course, when you are tuning, when you separate the distance between the plates, what happens to capacitance? It decreases, right? You remember? Good. So as you are tuning, you are increasing or reducing the separation distance between the two plates in the capacitor, and then at the end of the day, you find yourself having variable signals which you can turn into. Now, something amazing also takes place at times. Have you ever noticed that when you're tuning to a particular station, you discover that you are hearing almost two stations at the same time? One station is speaking, the other one is speaking. Yes, such thing happens when resistance is very high in the circuit. At high resistance, maximum current becomes very close to the instantaneous current of a particular station. And because they are very close, you now have resonance taking place between them, and you find yourself listening to two stations almost at the same time. All right, so basically that is that for resonance. So that takes us to the 16th fact, which is in the power, which is power itself. Okay, first, power in an AC circuit is simply the product of current, voltage, and cos phi. Cos phi is simply the power factor rating. And that power factor rating determines how poor or how good a circuit is in terms of power consumption. And the value of cos phi ranges from 0 to 1. The closer it is to 0, the more poor, if there is a word like that, the circuit is in terms of power consumption. The closer it is to 1, the more effective the circuit is in terms of power consumption. Okay? Good. So it is also important for you to know that for a purely resistive circuit, impedance and resistance are in phase. In other words, the angle between impedance and resistance is 0. And because it is 0, cos phi becomes cos 0 degrees, which is 1. And that system becomes a very powerful power consuming system. Beautiful. All right, that takes us to power absorption. Power absorption simply means a particular component in a circuit absorbing power. Let me use that word in a layman's language. A component in a circuit absorbing power, you refer to it as power absorption. And the gospel truth about it is that only resistors are good in absorbing power in a circuit. Inductors do not absorb power. Capacitors do not absorb power. They can store energy, but not power. That's what you have to understand. So now, if you have a circuit that is purely inductive and you are expected to calculate probably the power absorbed by the system, you don't even need to calculate. It's simply 0. Why is it 0? Power is simply IV cos phi. Good. Now, here, if you further derive that formula, you have I square R cos phi. Then I is the current flowing. Because there is no resistor in the circuit, since it is purely inductive, 0 is the position of R cos phi. And when you do that multiplication, it gives you 0. Automatically, there is no power absorbed in a purely inductive circuit or a purely capacitive circuit, as the case may be. So take good note of that. That takes us to the 17th fact, which is the power in a purely inductive circuit. Yes, I want to now go into details of the formula of the power in a purely inductive circuit. First, you will agree with me that in an inductive circuit, voltage leads. And because voltage is leading, the instantaneous voltage is V equals to V naught sine WT plus 90 degrees, okay? And then, of course, current, instantaneous current is I being equals to I naught sine WT. Substitute that in the formula for power, which is IV. By the time you do that substitution, obeying the laws of trigonometry properly, you will end up with power being equals to half the product of I naught V naught sine 2WT. And this is the power in a purely inductive circuit. Now, take note, if you look at this formula, there is no inductance in the formula, okay? And that simply means that inductors absorb no power. But that does not mean that the circuit does not generate power, okay? Power is generated in the circuit, but there is no absorber in the circuit, which is purely inductance. All right, so that takes us to the power in a purely capacitive circuit. The same thing applies. The instantaneous voltage in a purely capacitive circuit has minus 90 because voltage is lagging, right? So V becomes V naught sine WT minus 90 degrees. I is I naught sine WT. And when you substitute that in the formula for power, which is IV, obeying the laws of trigonometry, power becomes a half I naught V naught sine 2WT. Same formula as you have in a purely inductive circuit. And this is a proof that capacitors or inductors do not absorb power. Okay, good. So that takes us to 19, the fact, which is the 19th fact, and that is on transformers. Yeah. What is a transformer? A transformer is simply a device that can step up or step down voltage, okay? It comprises of primary and secondary windings won by the same core, right? Now, the primary coils are always referred to as input coil, while the secondary coils are referred to as output coils, as the case may. Input voltage, while the secondary coils are referred to as the output. Do you understand what I mean? I'm a little bit trying to be fast because this is already 40 minutes, okay? I don't want it to delay too much. So basically that is that. When the primary coils are more than the secondary turns, what happens? You call it a step-down transformer. And when the number of secondary happens to be more than the number of turns in a primary, you call it a step-up transformer. You can see those two diagrams and they can make things easier for you to understand. Efficiency of a transformer. The efficiency of a transformer is simply the ratio of the power output to the power input times 100 all over 1. Okay? So that takes us to the last fact, which is the conservation of energy in a transformer. And that is fact number 20. Conservation of energy in a transformer. When energy is conserved in a transformer, the power output and the power input becomes equal. That shows that energy is conserved. If the amount of power entering the transformer is 100 watts and the same 100 watt is leaving, that is a purely conservative transformer. And when that happens, you discover that P in becomes equal to P out. So the current in the primary and the voltage in the primary becomes equal to the voltage in the secondary and the current in the secondary. So IP there signifies primary, the current in the primary coil, while VP is the voltage in the primary coil. VS is the voltage in the secondary coil. IS is the current in the secondary coil, as the case may be. And then it's also important for you to know that when the number of turns becomes very, very important, the number of turns increases with increase in voltage. Let me break it down in this way for you to understand better. First, voltage is inverse to current. That is why IPVP equals ISVS. Voltage is proportional, directly proportional to number of turns. In other words, the higher the number of turns, the higher the induced voltage, right? So on that note, VP NS becomes equals to VS NP. And then also, current is inverse to the number of turns. The higher the number of turns, the lower the current. And then at the end of the day, what do you have? You have IP NS being equals to IS NP. Now, the reason why you have to understand this jurisdiction is because at times they can relate voltage and number of turns, or relate current and number of turns, or relate voltage and current only. So you should be able to know how to play your game. Wow, ladies and gentlemen, we have gotten to the end of this chapter. Yeah, AC circuits is over now. So we have done justice to this chapter. Thanks for listening. Thanks for taking time to listen to this video or audio podcast. May the good Lord bless you with a strong retentive memory, and see you in our next chapter, which is chapter 11, and that is atomic structure, right? Modern physics, so to say. Boom.